Hi guys, welcome to my YouTube channel, and in this video we're going to discuss intermolecular forces. So intermolecular forces are forces of attraction that result from the covalent bonding between two molecules. So they are of different types. They are weak intermolecular forces and also strong intermolecular forces. They are examples of weak van der Waals forces that are between one molecule and another molecule. So one type is the instantaneous, which is temporary, dipole induced dipole forces, which are also known as the London dispersion forces. And then you have the permanent dipole forces, which include the hydrogen bonding. So to know the bonding between two molecules, for example, there are type of force which is ionic bonding, and then the strength of the bond. You find that ionic bonding are strong, followed by OH covalent bonding, then the hydrogen bonding, and permanent dipole forces, and then in instantaneous dipole induced dipole forces of attraction. So before we look at the forces of attraction first, the intermolecular forces, between the intermolecular forces, then you're going to look at electronegativity, because electronegativity is the one that makes the forces of attraction between two molecules to be possible. So electronegativity is basically the power of an element or of an atom to pull the electrons towards itself when it's bonded to another atom. So the greater the electronegativity value, or the greater the electronegativity the atom is or the element is, then the greater the amount of force it is going to pull or attract electrons towards itself. So you find that electronegativity increases across the period from group 1 to group 7, and you find that elements in group 7, they are the most electronegative elements, with fluorine being the most electronegative element. So you find electronegativity increases again up the group. So you find fluorine is the most electronegative element, followed by oxygen, then followed by nitrogen, chlorine, and later on bromine. So there are factors that affect electronegativity between elements. For example, the nuclear charge, which is the force of attraction that is mostly present in the nucleus, the positively charged nucleus. So the more the nuclear force, the nuclear charge, then the more electronegative an element is. Then the atomic radius, which is of the distance between the nucleus of the atom and the electrons in the outermost energy level of the atom. And then the shielding effect. Therefore, the greater the shielding effect, or the greater the number of shells and subshells, then the less the nuclear charge that is in the atom. So then you are going to look at the ionic or whether the bond is ionic or covalent, and we use a scale that is known as Pauling electronegativity scale to determine the electronegativity values of elements. So the table shows that lithium has electronegativity of 1, it has a scale of 1, beryllium 1.5, all the way to chlorine, which has 3.0 electronegativity in the Pauling scale. So carbon, for example, has 2.5 and nitrogen has 2.1, and you find that they are the ones that have less they have less electronegativity units value in the Pauling scale, and this Pauling scale does not have units. So if it's 3.0, it's just that 3.0. So the difference in electronegativity values between two elements can be used to predict whether the element has ionic bonding, whether it has covalent bonding, or if it has which kind of bonding, in short. So for example, if the electronegativity value is 2 or more than 2, it means that that atom has ionic bonding. For example, sodium chloride. it has the electron, sodium has 0.9, chlorine has 3.0, so the difference between 3.0 and 0.9 is 2.1, therefore it has ionic bonding. If the electronegativity value is below 0, then you find that atom or those molecules have covalent bonding. The two of them have covalent bonding. For example, carbon with the 2.5, hydrogen with 2.1, the difference is 0.4. It's below 0.1, therefore they have covalent bonding. If the difference is 0, then there is no ionic character in those molecules. For example, if it's bonding between chlorine and chlorine, then the electronegativity difference is 0. And therefore you find that they do not have any ionic character between them. Then you are going to look at polarity of molecules, and electronegativity values between two covalently bonded atoms. Then you find that if one covalently bonded atom is more electronegative than the other, it is going to pull electrons towards itself. So the more electronegative atom pulls more electrons towards itself, and as a result you find that the negative charge is distributed, or electron distribution is asymmetrical, and then the more electronegative atom therefore has the partial negative value, while the less electronegative atom has a partial positive charge. And with that, having a partial negative charge and partial positive charge, we say that that bond formed is a polar bond, or it is a dipole. It has two poles. So as the electronegativity difference between two atoms increases, then the bond becomes more polar, and the degree of polarity of a molecule is measured using a dipole moment, a moment between the two polar points. So the direction of the dipole is shown using a sign that is displayed there in my video. Then you find that the arrow normally points towards the most negatively charged atom, or the end of the most negatively charged element of the two. So in molecules containing more than two atoms, then we have to take into account the polarity of each bond and then the arrangement of the bond in that molecule. So for example, in trichloromethane, that is methane that has 3 chlorine bonded to a carbon molecule, and you find that there are 3 carbon chlorine dipoles. One carbon is partially positive, chlorine is partially negative, so they are pointing in a similar direction, and therefore their combined effect is not cancelled out by the polarity of carbon hydrogen bond, because now carbon hydrogen bond is not polar, or it's virtually non-polar. The electron distribution is asymmetric in that manner. And then if you have another molecule that is polar, for example, another molecule, for example, tetrachloromethane, which has 4 chlorine molecules bonded to each other, you find that molecule is non-polar. Yes, it has the polar bond between carbon and chlorine molecules, but then those the bonds cancel out, and therefore you find that the tetrachloromethane is non-polar, though it has the polar bond between carbon and chlorine molecules. So the bond polarity influences its chemical reactivity. So for example, if you have 2 molecules, nitrogen, both of them have 3 bonds. Nitrogen bonded to another nitrogen in 3 bond, and nitrogen is non-polar. Then you have carbon dioxide, which has carbon covalently bonded to oxygen using 3 bonds. Then carbon monoxide requires a lot of energy to break, because it is a polar molecule. It has a partial positive charge on the carbon and a partial negative charge on the oxygen molecule. So that is why you find that carbon monoxide is highly reactive as compared to nitrogen, which is like unreactive. So you find that many chemical reactions are started by the reagents attacking one of the electrically charged atoms or ends of the polar molecule, e.g., in this molecule that is displayed. You find that the attack is possible in ethane because there is a partial positive charge between a carbon and the chlorine molecule. Let's look at instantaneous dipole induced dipole forces. The instantaneous dipole induced dipole forces, they are present in gases, for example, the noble gases, neon and argon. So you find that some of them are liquefied, but at very low temperatures. So that means there are weak forces of attraction between the atoms. And these weak forces of attraction normally keeps the atoms together in the liquid state. So, for example, bromine is an nonpolar molecule, and it is normally a liquid at room temperature. It has weak forces of attraction that keep the bromine molecules together at room temperature. Those weak forces of attraction, they are called instantaneous induced dipole induced forces or dispersion forces, and they normally exist between two molecules. So the electron cloud in this nonpolar atom, they are constantly moving, and you find that at one point they are concentrated on one end and another point they are concentrated on another. So that means that there is creation of a temporary dipole setup, for example, in a bromine molecule. And this dipole setup, it makes one of the atom to be more electronegative than the other. So at that point you have a dipole moment between these two, but it is temporary because the electrons are in constant motion. That is why you have an instantaneous dipole induced dipole force of attraction, for example, present in bromine, where one of the bromine electrons tend to be moved towards one bromine, which tends to have a partial negative charge than the other. So the dipoles are always temporary because the electrons are constantly moving, and therefore they are called the instantaneous dipole induced dipole forces of attraction. So they increase with increase in number of electrons or protons in a molecules, and increasing in the number, or they also increase with increase in number of constant points between two molecules. So the differences in size of these instantaneous dipole induced dipole forces can be used to show the enthalpy changes of vaporization between 2 points of noble gases. So I have a graph that shows that. So you find that due to increase in number of electrons, then enthalpy of vaporization also increases. So it is high in helium, it is low in helium, and then it increases as the number of electrons increases up to xenon. So then the more the number of electrons, then the higher the instantaneous dipole induced dipole forces of attraction in those molecules. So also you can also see in the next graph that the boiling point of noble gases increase as you go down the group from the smallest to the largest. So this is because of increase in instantaneous dipole induced dipole forces of attraction between those molecules of the noble gases. So the more the number of electrons increases, then the higher the instantaneous induced dipole forces of attraction also increase. So also the increase in number of contact points, when you compare two contact points between molecules, the more the number of contact points, then the higher the boiling point as a result of increase in number of those temporary forces of attraction. So for example, if the boiling point of pentane is 36, while the boiling point of 2,2-dimethyl-propane is 10 degrees Celsius. So this compound, they have the same number of electrons in their molecules because they are just almost similar. And then you find that pentane has higher number of contact points, and therefore the instantaneous dipole induced forces are stronger than those in the 2,2-dimethyl-propane because of increase in contact point between two neighboring molecules of this pentane molecule. So another example can be explained by looking at polythene. So there are normally two types of polythene. There is low density polythene and there is high density polythene, which both have crystallization, and another one is non-crystalline. It has crystalline region and non-crystalline region. So higher density polythene has many crystalline region, and therefore it has many contact points, and that is why it has higher boiling point, or it has high instantaneous dipole induced dipole forces as compared to the low density polythene, which has lower which has less crystalline region and therefore low instantaneous dipole induced dipole forces of attraction.